In this unit, we're going to discuss two-frame structure for motion, which is the most basic setup where we're given just two images taken from different viewpoints, and we want to find the relative motion between the two cameras, as well as the location of the 3D points that correspond to the projections that we observe in the images. And I have to say that being able to reconstruct 3D from just two images, two flat images of a scene, is something that has always fascinated me and was triggering me to enter that field. And I still find it fascinating that it's possible today. Now, in order to do this, we first need to understand so-called apipolar geometry. Again, the goal is to recover now from just two images and detected features and matched features in these two images, the relative camera pose between these two images or cameras, and the 3D structure from just these image correspondences that we have detected, for instance, using the SIFT descriptor from the last unit. And the required relationships are described by the two-view apipolar geometry that's illustrated here on the right. Okay, so what do we have here? We have two cameras. This is the camera center of the first camera and the image plane of the first camera center of the second camera, and the image plane of the second camera. And the rotation matrix R and the translation vector T denote the relative pose between these two cameras. And we assume that we have two perspective cameras. So this is a pretty realistic assumptions that we're having here. Almost all standard cameras follow that model. We have removed distortion. We can model them like this. Now, a 3D point is projected into the left image onto pixel x bar 1. We're using this augmented vector here, which is just to recap the homogeneous vector where we normalize by the third component such that the x and y pixel coordinates can be directly read off from the first two components, the first two elements in that vector. And similar, that 3D point gets projected into the second image onto pixel x bar 2. Now, the 3D point and the two camera centers form or span the so-called apipolar plane. Because we have three 3D points, all of them must lie on a single plane, that's clear. But because the points get projected linearly into the images, we also know that the pixels x bar 1 and x bar 2 lie exactly on the same plane. All of these 5 points, 3D point, the camera centers, and the pixels, lie on the so-called apipolar plane. And now, one nice property of this apipolar plane is that if we have already recovered that apipolar geometry and we know the apipolar plane, then this restricts the search space when we want to find the correspondence of one particular feature point in the first image in the second image. And why is that? Well, if we have such a point, x bar 1, for which we want to find the correspondence in the second image, we do not have to search through the entire 2D image domain in order to find that point. But we know from the apipolar geometry that that point here must lie on that apipolar plane. And in particular, it must lie on the so-called apipolar line that is the intersection of that apipolar plane with that image plane here, second camera. And that's indicated here by homogeneous L2. This is the so-called apipolar line, and that apipolar line exists also on the other image. If we want to find the feature that corresponds to x2 bar in the second image, we want to find that in the first image, we need to search only along the apipolar line L1 in the first image, and not everywhere in the first image, just on this, along this 1D search space. And this is, of course, a significant simplification of the problem, of the search problem. once we have found the apipolar geometry, once we know the camera, the calibration, and also the relative pose between the two cameras. And this is used ubiquitously across all 3D reconstruction techniques that produce state-of-the-art sparse or dense 3D reconstructions. And we're going to cover some of them at the end of this lecture, so-called multi-view stereo techniques. Very briefly, just showing some results, but we're going to discuss in more depth in terms of two-view dense stereo reconstruction techniques in the next lecture, and then also as some applications of graphical models, for instance, in later lectures. So this is the point of the apipolar geometry. Once we know the camera calibration matrices and the rotation and the translation, then finding correspondences suddenly becomes much easier. But in order to recover the apipolar geometry, which we're going to discuss next, we need to find correspondences without knowing the apipolar geometry, of course. So we need to search sparse feature correspondences across the entire image domain. We need to solve a harder problem in order to find these few parameters of the apipolar geometry. There's actually, the camera calibration is known, there's 5, 3 for rotation and 2 for translation, because there's a scale ambiguity left. So we only need to find these 5 parameters, and then the search problem becomes suddenly much easier. And then it becomes also clear that all these apipolar lines for all possible 3D points pass through a single point in the 2D image planes, which is called the epipole. So we have one epipole in the left image plane and one epipole in the right image plane. And that is exactly where the so-called baseline, the connection between two camera centers, passes through the image plane. And that doesn't need to be on the image plane. That can also be at infinity if the cameras are oriented in the same direction. But here in this example, they are in the image plane. So to see that actually all epipolar lines pass through these two epipoles, I have drawn another point here, another 3D point, and also the epipolar plane and the epipolar lines and the epipoles for this plane here. And you can see if I'm moving that 3D point, then the projections, of course, of this 3D point change and the epipolar lines change. But the epipolar lines always pass through these epipoles that stay fixed. Good. So now the question is, how can we mathematically express that relationship and how can we recover that relationship? So let's start by assuming that we know the camera matrix of the left camera or the first camera and the second camera, AI, which is a 3x3 matrix. And we know that, for instance, through calibration techniques that we've discussed in the first unit. Now, if we know that calibration matrix from a 2D pixel coordinate here in augmented vector notation, we can find the local ray direction by undoing what the last step of the image formation process does, which is the camera calibration matrix application. We're just doing the inverse of that. So we have the local ray direction in 3D space of that pixel x bar, and we call that x tilde here because it's an homogeneous coordinate, but we're not using any further subscripts here just for simplicity. So this is the local ray direction by just multiplying the pixel with the inverse of the calibration matrix, just undoing this last step of the projection. Now, what we have is that this local ray direction must be proportional to the 3D point, because the 3D point is on that ray, just at a different distance. We're using that symbol here to denote proportionality. Now, what we also know is that this 3D point is related, that 3D point with respect to the second camera system, represented with respect to the second camera system, is related to the same 3D point represented in the first camera coordinate system, which we denote by x1 here, through a rigid body transform, because we're going from this camera coordinate system to this camera coordinate system with this rigid body transform. So this point which is x1 in this coordinate system, becomes x2 in this coordinate system by multiplying it with r and translating it with t. This is this here expression. Now this one here is proportional to this expression here, because there's only a scaling relationship that we have introduced here. So we have changed x1 to x1 tilde, which is the local ray direction in the first camera. And because we have just scaled this, we of course need to apply the same scale here on the right hand side, which I just denoted by s multiplied to t. That's basically the proportion of how much we have scaled x tilde with respect to x bar 1. Now, what we can do with this is we can take the cross product of both sides with t and obtain the following expression. So if we take the cross product of this side here with t, we have this expression here on the left side. And then here on the right, if we take the cross product, we have this expression, because the last expression is the cross product of t with itself, which is 0. So this term falls away, no matter what s actually is. Now what we can do for on is we can take the dot product of both sides, again on the left side here, with x tilde to transpose, which yields the following expression here. We have x tilde t, x tilde cross product t, so this is the skew symmetric matrix we've introduced in the previous lecture, r x tilde 1. And this must be proportional, so we have swapped these two expressions here, left and right, to x2 t and the cross product is skew symmetric matrix of t, x tilde 2, this is this term here. Now, on the right hand side here, what we have here is the so-called triple product. It's an inner product and a cross product combined. And what we know from the triple product, because it describes the volume of the trapezoid that's represented by the three vectors, is that this volume is 0 if two of these vectors are the same. This is just a geometric property that you can also look up on Wikipedia. So if two of these vectors are the same, then this must be 0. So the entire expression here on the right hand side is 0. And because that's proportional to the left hand side, no matter what that proportionality is, the left hand side must also be 0 to fulfill this in general. So we have retrieved this expression here. We have retrieved an expression for the local ray directions, relating the local ray directions in the first image and the local ray direction in the second image through this matrix here. And this is the so-called apipolar constraint. X tilde 2 transpose E, this is called the essential matrix. X tilde 1 equals 0. And the essential matrix is simply this skew-symmetric matrix from the translation vector multiplied with the rotation matrix of the relative pose between the two cameras. Now what we see from this expression here is that this is actually also leading to the apipolar lines directly, because E maps a point x1 in image 1 to the corresponding apipolar line in image 2. And so if we take this E and we multiply it with x1 tilde, we obtain a line expression, because x2 tilde transpose L tilde 2 is equal to 0 because of the apipolar constraint that we have derived. This is just, if I plug this in here, I get the apipolar constraint. And here I have the line equation. And that means if I multiply to that line, to that E on the right hand side, x tilde 1, then I have just the covector. We called it before the covector here, that together with another point, x2, equal to 0, represents the line constraint. All points x2 are on the line if multiplied with L are equal to 0. And similarly, by transposition, we obtain the opposite. We obtain the apipolar line in image 1 as, now transposing this expression here, E transpose x2 is the line, the apipolar line in the first image plane. Right, and here's the relationship again, just visually. Now, for any point x1 in the first image, the corresponding apipolar line in the second image passes through the so-called apipole. That is what we know from just the fact that all of them are on the same apipolar plane. And therefore, the apipole satisfies the following expression. The apipole multiplied with the apipolar line, because the apipole must be on the apipolar line, is equal to 0. And here's the expression for the apipolar line. So E2 transpose E tilde x tilde 1 must be equal to 0. And this must hold true for all possible x1s. Right? So for all possible x1s here, the apipole E2 must be on the apipolar line L2. For this one here and for this one here. And this gives us a constraint for where that apipole must be located. It follows that if this has to hold true for all x1, then actually this left-hand side here must be equal to the 0 vector. Otherwise, this couldn't hold true for all x1. So E2 transpose times the essential matrix is equal to the 0 vector. And from this expression here, we can directly read off that E tilde 2 transpose, so the apipole in the second image, is the left null space, or in other words, the left singular vector corresponding to singular value 0 of the essential matrix. And similarly, we have that the apipole in the first image is the right null space, or in other words, the right singular vector with singular value 0 of essential matrix. It's just given here by expression. So, good. So we know how we can extract the apipole, for instance, from the essential matrix. But how can we recover actually the essential matrix from the image correspondences? Well, let's assume we have n image correspondences and SIFT features in the left image that have been matched to SIFT features in the right image. Or first image matched to features in the second image. Now, with these correspondences, we can form n homogeneous equations in the 9 elements of this essential matrix, because we have this constraint here, which gives us exactly one equation for each correspondence. And if we write this out, we get this equation here for each of the correspondences, and see that here we have the elements of the left and the right pixel coordinates, x1 and x2, x1 and y1, and x2 and y2, and we have the elements. E11 is the first element of that essential matrix. We have one equation now for each image correspondence in terms, and you can see it's linear in terms of the elements of the essential matrix. It's a homogeneous equation. Now, as E, the essential matrix, is a homogeneous matrix, we have to constrain again, as in the case of estimating homographies in the last lecture, the scale of that matrix, and we can constrain that scale of the matrix to 1 by again using singular value decomposition and obtain a solution to this system, to the constraint system. It's exactly the same way as we did it for the recovery of the homogeneous of the homography before, and you will see that exactly the same trick we're going to apply multiple times also throughout this lecture here. So it's a very important trick. Now, one thing to note here is that in this equation, some of the terms are products of two image measurements, and some of them are just products of one image measurement. And this introduces some asymmetry. And if you have measurement noise, this amplifies measurement noise. And to counteract this, the normalized 8-point algorithm from Hartley, a seminal paper called In Defense of the 8-Point Algorithm, I recommend reading, normalizes the image features in the 2D image plane. It particularly widens them to have zero mean and unit variance, and then runs the recovery algorithm for the essential matrix. And then after the recovery, this normalization can be undone in analytic form. And it turns out if you do that, then you get much more stable results. So it's a good idea to always do that. To first normalize the image coordinates such that they have zero mean and unit variance. And then you do the SVD, and afterwards you're undoing this normalization again. And you get much more stable results. Because in practice, your SIFT correspondences are always going to be contaminated by noise. And so this effect will be much less strong if you do that. Now from this essential matrix, now we have recovered the essential matrix elements. But how can we recover the rotation and translation from that? Well, to recover the direction t hat of the translation vector t, and we can only recover the direction because the scale is not uniquely determined. You can also show that from the two images alone, because you can scale the reconstruction and you can scale the translation vector, and you still get valid reprojections into the image into the image planes. So there's an ambiguity. You can't measure this. But we can recover the direction, which we call t hat, by multiplying t hat transpose to the essential matrix, because we have t hat transpose times the skew symmetric matrix of t times r, and this is 0. The entire expression becomes 0, and therefore first of all, therefore the essential matrix is singular, so there's one singular value that's 0. And we obtain t hat as the left singular value associated with the singular value 0. But in practice, of course, because we have measurement noise, the singular values will not be exactly 0 due to this measurement noise, and therefore we choose simply the smallest one. If you look at the singular value decomposition, one singular value should be very close to 0, and the other two are actually quite equal to each other. And if you see that, then you just pick the one that's closest to 0. Now the rotation matrix can also be calculated from this expression, but it's a bit more complicated and technical, and there's multiple solutions. So we're not going to cover this in detail in this lecture, but if you want to know more about it, you can read up on this in the Zelinsky book, chapter 11.3. Final remark, the essential matrix has 5 degrees of freedom because there's 3 for the rotation and 2 for the translation, as we don't know this absolute scale, but just the direction. So in theory, you don't even need 8 correspondences. You can get away with less, and there's algorithms for computing this with less correspondences, so they are not as simple as just a singular value decomposition as we have done here. Now, there's another important matrix that we're going to quickly cover, and that's also covered in this song here that I recommend to watch, is the so-called fundamental matrix. And that is relevant if the camera calibration is unknown. If the camera calibration is unknown, we cannot use the local ray directions, but we have to use the pixel coordinates directly. And therefore the essential matrix from before becomes this. Right? We know that the local ray directions are defined as such. x1 is equal to k1 inverse x bar 1. This expression here, and the same for x2, here just transposed. And so we replace this here, and the fundamental matrix then directly relates the pixels, not the ray directions, because we don't know k. And the matrix that is relating these two is now called F and not E anymore, but it contains E and these two inverse calibration matrices. in one single 3x3 matrix, and this is called the fundamental matrix. Like the essential matrix, the fundamental matrix is, in absence of noise, rank 2, and the epipoles can be recovered in the same way as before. However, the intrinsic parameters cannot be directly determined. In other words, we obtain only a perspective reconstruction and not a metric one. And that's not very desirable. But it's still useful in order, for instance, to do certain verification tasks for verifying if feature correspondences are actually correct because they lie on the apipolar lines. You can do that, but you don't get a metric reconstruction. But if you have some additional information like vanishing points, you know that k is constant across time for all the frames you have, there's some information about the intrinsics, then you can actually upgrade the perspective reconstruction to a proper metric one, and there's a couple of papers on this topic as well. So here's an illustration of how the apipolar geometry looks like, independent of, we know just the essential matrix, or we know the fundamental matrix. Here we have the apipolar lines that correspond to each other, and you can note here that, for instance, for this point here that is corresponding to this point here, we have all the correspondences aligned here, all the hypothetical correspondences, all the hypotheses are aligned on the apipolar line. So we just need to search along the apipolar line to find the corresponding point for this point here. In this case, this would be the correct correspondence. Okay, so now we have recovered the relative or the relationship between the two cameras in terms of their rigid body transform up to scale, but we haven't recovered the 3D points location yet. And this is done through triangulation. Now, given these two cameras with intrinsics and extrinsics, how can we recover the 3D geometry? And well, that's pretty easy. Now, given these two and given correspondences, we can just shoot the rays into 3D space and we can see where they intersect. However, because these measurements, these SIFT correspondences are typically noisy, these rays might not intersect precisely. And we need to take that into account. So we want to recover a point, 3D point, that in some sense is closest to these two rays. Okay, so let x tilde w denote a 3D point in homogeneous coordinates. We could also write x bar but because we can't recover x bar, we're writing x tilde here directly. And that is related to the point on the image plane. And now we're introducing, to distinguish these two, we're introducing the s as an index. So this is the 2D pixel coordinate in homogeneous coordinates. And they are related to this through this 3D projection, as we've introduced in the last lecture. This is the projection matrix, 3D to 2D projection. So this is the equation for projecting this 3D world point xw onto the image of the IF camera. And as both sides are homogeneous, they have the same direction but may differ in magnitude, and we are applying the same trick as before for estimating homographies if we want to recover now from this relationship xw. So to account for this, we consider the cross product again, and we know that the cross product is 0 if these two are the same up to some unknown scale factor. So this is the constraint that we're concerned with. And now if you write this out and use PIK to denote the kth row of the IF camera's projection matrix, you obtain a linear equation like this that is linear in the unknown that we want to recover, which is the 3D point location in homogeneous coordinates. So you can try this out yourself. Very easy to see that this corresponds. So this can be derived from this. So what we have here now is one constraint per image, I. So I is the image index. And because we want to find, and because we have two constraints here, actually two constraints. So this is 0 vector, and we have one constraint for the x coordinate and one for the y coordinate. But because we have a 3D vector to recover, we need two correspondences to identify the 3D point. And that's also clear by looking at this image. If I just have one camera, I can't recover the 3D point. I need at least one more. But it's of course better to have more cameras to recover that point more precisely. So you can add as many equations, you can stack as many equations to this linear system as you like. This is just giving you 2 constraints, but you can have 4, 6, 8, 4. So stacking n with n equal or bigger to 2 observations of a point, we obtain a big linear system, a x tilde w equals 0. And as x tilde is homogeneous, this leads again to a constrained least squares problem, where again the solution to this problem is the right singular vector corresponding to the smallest singular value of a. And this is exactly the direct linear transform we're already familiar with from lecture 2 for homographies, but now for estimating the 3D point location. Some remarks. While DLT often works well in practice, it is not invariant to perspective transformations. That means that noise that happens in the image is not taken appropriately into account. And therefore the gold standard algorithm is to do something else, is to minimize the reprojection error, to find the 3D point that when projected into the 2 or more images is giving the smallest Euclidean distance in the image plane. And we can formulate this as such an optimization problem that can be solved using numerical gradient-based techniques such as Liebenberg-Marquardt. So here we have this notation denotes xs is the projection of the 3D point xw, here with the bar for the denote an augmented vector, and xo is the observation. We're trying to minimize the projection minus the observation discrepancy. And we're doing this over all the observations of all the cameras for that particular point, and we're optimizing over that 3D point. You can see that the point is not having an I index because it exists only once, but we have n different observations, so the projection and the observation depend on I because we have different projection matrices and different observations in the different images. And now this allows us to take measurement noise appropriately into account. For instance, if we have Gaussian measurement noise in the images, this is the right model to use. If we have different noise models, we can also incorporate them here. But this is what is typically done. The minimum can also be obtained in closed form as the solution of a 6-degree polynomial. But this becomes more technical then. More details on this can be found in the textbook from Hartley and Sisserman, section 12.5. Now, triangulation works differently well depending on the relative camera pose. And there's some trade-off. So here you can see the shaded region denoting the uncertainty, basically the area where the 3D point could be located. And that increases as the rays become more parallel to each other. See that here. So if you have this situation, then you have a very small gray region, but then in this situation here, you have a very elongated gray region. And so the uncertainty is very high. And there's a trade-off here because if you're looking at the scene from 2 different perspectives, then feature matching is very hard because the images look very different locally. But the triangulation will be better. And for nearby views, it's very easy to match features because the features look similar, but triangulation is harder or more uncertain, to be precise.